2 weeks ago, on July 31st, 2026, a telescope in the Chilean Andes released an image that scientists have been waiting 20 years to see. It was not taken last week. It was built from hundreds of individual observations stacked on top of each other over months of commissioning work, combined into a single composite view through a process called co-addition. The astronomical equivalent of taking 1,000 photographs of the same scene and layering them until the faintest details emerge from the noise. And when the final image appeared on screens at research institutions around the world, the reaction from astronomers was not the calm, measured response of people who had been expecting this. It was the reaction of people who had spent their careers imagining what this instrument would show them, and who were now seeing, for the first time, what they had imagined was actually an underestimate, packed into a single frame, a single view of one patch of sky in the constellation Sextans, a region that astronomers have been studying for more than 2 decades because its precise location in the sky makes it ideal for deep cosmological observation for more than 650,000 galaxies, 650,000 separate island universes, each containing hundreds of billions of stars visible simultaneously in one image, and more than 50,000 foreground stars belonging to our own Milky Way scattered across the frame like grains of sand. The image covered approximately 3,000 square degrees of sky, roughly 1/6 of the entire visible southern hemisphere. And it was, as Rubin Observatory director Bob Blum stated plainly in the release, just the beginning. The region of sky captured in this image is called the Cosmos Field, the Cosmic Evolution Survey Field. It is not a random patch of sky. Astronomers chose it specifically in the early 2000s because it sits away from the cluttering foreground emissions of the Milky Way's own gas and dust, giving a cleaner line of sight through to the distant universe. The Hubble Space Telescope observed it. The Spitzer Space Telescope observed it. The Canberra X-ray Observatory observed it. The Subaru Telescope, the Very Large Array, the European Southern Observatory's instruments, over 2 decades, essentially every major observatory on Earth and in space has contributed observations of the cosmos field, building up a multi-wavelength catalog of more than 2 million galaxies that has become one of the most scientifically rich datasets in the history of astronomy. The cosmos field contains over 2 million galaxies that span across 75% of the age of the universe, with some as far as 12 billion light-years away. 2 million galaxies spanning 75% of cosmic time, from nearby spirals to ancient red smudges at the edge of the observable universe, all in one patch of sky. When Vera Rubin Observatory pointed its 3.2 gigapixel camera at this field and released its first science image 2 weeks ago, it added its own layer to that catalog. And what it added was different from what anything before it could provide. Not just depth, not just resolution, but the dimension of time. Packed into this single image from Rubin Observatory are many different kinds of galaxies. Spirals with delicate arms, smooth elliptical galaxies, distorted merging galaxies, and faint red galaxies from the distant universe. That variety, galaxies at every stage of their evolution, at every distance, in every configuration, is precisely what makes the cosmos field so scientifically valuable. A spiral galaxy with delicate arms is a galaxy still actively forming stars, its disk of gas and dust being sculpted by density waves and gravitational interactions into the beautiful pinwheel structures that define the most visually striking objects in the cosmos. A smooth elliptical galaxy is a galaxy that has largely stopped forming stars. It has consumed its gas reservoir, either through star formation or through being expelled during mergers, and is now aging gracefully, its stars reddening as the most massive ones die and the lower mass ones burn on for billions of years. A distorted merging galaxy is a galaxy in the process of colliding with another, its shape temporarily deformed by the tidal forces of the collision, its star formation rate briefly elevated as the gravitational disturbance compresses gas clouds and triggers new stellar births. And a faint red galaxy from the distant universe is a galaxy seen as it was billions of years ago, its light redshifted into longer wavelengths by the expansion of space, its appearance frozen at a moment deep in cosmic history. All of these simultaneously in one image, a complete cross-section of galactic evolution from the present to within 12 billion years of the Big Bang. The terrifying aspect of this image is not what it contains, it is what it implies about what Rubin will find as the full 10-year survey proceeds. The Cosmos Field image, released on July 31st, 2026, covers approximately 1/6 of the visible southern hemisphere sky. It provides the Rubin science community with a deep co-added image covering 3,000 square degrees of night sky, which is around 1/6 of the entire visible southern hemisphere sky. 1/6, and it contains 650,000 galaxies. The full LSST survey will eventually cover the entire southern hemisphere sky, 6 times the area. At comparable or greater depth, returning to every region hundreds of times over 10 years, building up stacked images far deeper than this first release. The final LSST catalog will contain not 650,000 galaxies, but billions of galaxies. Not 50,000 foreground stars, but hundreds of millions. And critically, it will contain the time dimension that static images cannot capture. Because Rubin will image the same galaxy on Monday night, then again Thursday night, then again the following Monday, continuously for a decade. Every change that occurs in any of those billions of galaxies, a supernova exploding, a black hole flaring, a tidal stream from a merger shifting position, will be detected, flagged, and transmitted as an alert to astronomers worldwide within 60 seconds of the observation. The image released 2 weeks ago is a postage stamp. The completed survey will be the entire world. The observatory's current efforts will be followed by a second phase, expected later this year, from which individual observations and specialized difference images will be produced, highlighting objects that exhibit changes across successive observations. Difference images are the key to understanding why Vera Rubin is transformative in a way that no static deep field image, however spectacular, can fully convey. A difference image is produced by subtracting one observation from a later observation of the same field. Everything that has not changed between the two observations cancels out. The static stars, the galaxies whose brightness has not varied, the background sky, and what remains is only the changes. A supernova that was not there on Monday but is there on Thursday appears as a bright point in the difference image immediately, identifiable and immediately alertable to the global astronomy community for follow-up. An active galactic nucleus, whose black hole has brightened slightly, appears as a faint enhancement at the galaxy's center. A near-Earth asteroid moving through the field appears as a streak, its velocity and trajectory immediately derivable from how far it moved between the two exposures. The Cosmos field image released 2 weeks ago is composed entirely of stacked detections, a beautiful summary of everything Rubin has seen in that region. The second phase of data release, expected in October to December 2026, will begin providing the difference images that turn a beautiful summary into a real-time alarm system for cosmic events. That second phase is what the astronomy community is actually waiting for, because it represents the beginning of what Rubin was fundamentally built to do. Once the LSST officially begins, the telescope will sweep the entire visible southern sky every 3 to 4 nights for a decade, imaging every accessible section of sky roughly 800 times and generating around 20 terabytes of data per night. 20 terabytes per night, 365 nights per year, for 10 years. The total data volume of the completed LSST will be approximately 73 petabytes, 73 million gigabytes of astronomical observations. To put that in a concrete comparison, the entire text content of the English language Wikipedia is approximately 21 gigabytes. The LSST will produce the equivalent of 3.5 million Wikipedias of astronomical data. No human team could read all of it. The analysis pipeline that processes Rubin's data runs automatically in real time, using algorithms developed and tested over years specifically to handle this data volume. Machine learning classifiers identify transient events and assign them to categories. Orbital fitting software computes asteroid trajectories from multi-night observations in minutes. Galaxy morphology algorithms classify each detected galaxy as spiral, elliptical, merging, or irregular based on the pixel pattern in each image. The human astronomers who study Rubin's data are not looking at raw images one by one. They are looking at the output of an automated analysis pipeline that has already identified the most scientifically interesting events from among the millions of detections made each night. Rubin does not just produce data. It produces a curated real-time alert stream of cosmic events happening right now, happening everywhere in the visible southern sky, classified and prioritized before any human has seen them. The dark matter and dark energy implications of the Cosmos field image are what the observatory was originally designed around, and they are what make the completed survey potentially the most important cosmological dataset ever assembled. Its goals include demystifying dark matter and dark energy, catching fast-moving or ever-changing objects in the night sky and mapping the universe around us. Dark matter makes up approximately 27% of the universe's total mass energy. It does not emit light, does not interact electromagnetically, and can only be detected through the gravitational influence it exerts on things that do emit light. When light from distant galaxies passes through concentrations of dark matter between those galaxies and Earth, the dark matter bends the light through gravitational lensing, subtly distorting the shapes of the background galaxies in a coherent pattern that traces the dark matter distribution. Measuring this pattern across hundreds of millions of galaxies, the weak gravitational lensing signal, requires exactly what Rubin provides: precise measurements of galaxy shapes at a depth and sky coverage that no previous survey could achieve. The Cosmos field image released 2 weeks ago already contains enough galaxies to begin this analysis in the small area it covers. When the full survey is complete, the combined weak lensing signal across billions of galaxies will produce the most detailed map of dark matter's distribution throughout the observable universe ever assembled, and that map will constrain what dark matter actually is at a physical level in ways that current observations cannot. With the launch of the 10-year legacy survey of space and time, the Rubin Observatory is opening a new window on the universe. The window it is opening is not just wider than any previous window, it is fundamentally different in kind. Previous observatories looked at specific places deeply or broad areas shallowly, but never both simultaneously. Rubin looks at broad areas deeply, and then looks again and again and again, building up not just a snapshot, but a history. The 650,000 galaxies in the Cosmos field image released 2 weeks ago will each be re-imaged hundreds of times over the next 10 years. Every supernova that explodes in any of those 650,000 galaxies will be detected within days of the explosion, providing the most comprehensive census of supernova rates and types ever assembled, black hole accretion physics that no previous survey could track on those timescales across that number of objects. Every galaxy emerger that begins or progresses during the survey will be documented in before and after imaging that shows the process of galaxy evolution in real time. The universe is not a static photograph, it is a movie. And the Vera C Rubin Observatory just pressed play.